And we are live. So hello everyone and welcome back to the Latin American Webinars on Physics. I'm Joel Jones from the PUCP in Peru and I will be your host today. This is webinar number 173 and we're having Jack Shergold as a speaker. Jack carried out his PhD at the IPP in Durham, UK, working with Martin Bawa on cosmic neutrino background detection. He is now a postdoc at IFIC in Valencia, Spain, focusing also on light-dark matter searches using quantum technologies, as well as some early universe cosmology. Today, Jack will give us an introduction on the cosmic neutrino background, and then we'll also give an overview on the proposals to detect this relic neutrino. We're very happy to have him as a speaker today. Now, before we begin, as usual, let me remind all viewers that you can ask questions and make comments via the YouTube live chat system. And then this question will be passed on to Jack at the end of the talk. So that's it. Please, Jack, go ahead.
Okay, so I can share my screen now?
Yes, please.
Okay, and everyone can see that just fine?
Perfect.
Okay, great. So, first off, thank you very much for the invitation. Yeah, it was interesting to get this invitation. I didn't know the series existed till I got the email, and I looked, and it's really quite a nice thing. So today I want to talk to you all a little bit about some stuff that I carried out during my PhD, where we looked at hunting for the cosmic neutrino background. So this project originally started, interestingly, as an attempt for us to put constraints on the cosmic neutrino background in the present day, because we realized that some of these constraints that you can place in the early universe don't necessarily apply in the present day, right? So you can say something about the cosmic neutrino background at the time of, say, the CMB or something along those lines, but if neutrinos decay, for example, the cosmic neutrino background might not be there in the present day. So we wanted to basically answer the question, what can we say about the CNUB in the present day? And it turned out that there weren't many things that we could say about it. So we then went ahead and thought, well, why not look at all of the different detection proposals based on what we do know about the CNUB today and see which ones are the most sensitive. So that's largely what I'd like to go through today. I want to talk to you all about the different proposals to detect the CNUB. The talk's going to be structured roughly like this. We're going to give everyone a very brief introduction to the CNUB, because I realize it's one of those topics that maybe a lot of people have heard about, but maybe not so many people have worked on, just to make sure everybody's up to speed. Then I want to talk about the general principles of cosmic neutrino background detection, and then I want to focus on 4 proposals specifically. I want to focus on the Ptolemy proposal, coherent scattering proposals, the Sadowski effect, and an accelerator experiment. So to get started, just a very brief introduction to the cosmic neutrino background. So what is the CNUB? So when we're talking about the cosmic neutrino background, we're interested in the period of the early universe, just after inflation, electroweak symmetry breaking, and the QCD phase transition, where we've got electrons, photons, and neutrinos all held in equilibrium through a combination of electromagnetic and weak interactions. And these are all at some common temperature, which we're going to call Ti. The universe expands and cools a little bit, to the point where one neutrino interaction takes roughly the age of the universe, and we have neutrino decoupling. This happens about 1 second after the Big Bang, which leaves us with 2 thermal baths, one of neutrinos and one of electrons and photons, which are still held in equilibrium through electromagnetic interactions. And importantly, at this point, the 2 thermal baths, even though they're no longer talking to one another, are still at the same temperature. However, this quickly changes as the universe expands and cools a bit more, so just below twice the electron mass. And you get electron-positron annihilation to pairs of photons. And if you go ahead and conserve entropy, you find that this reheats the photons slightly, leaving us with 2 thermal baths, now one of neutrinos at this same temperature Ti, and photons which are ever so slightly hotter at a temperature which we're going to call T gamma. The universe expands and cools a little bit more, and about 1 minute after the Big Bang, we get Big Bang nucleosynthesis, so the first atomic nuclei start to form. And then 10 to the 5 years later or so, we have recombination. So the last free electrons get locked up in atoms and photons become free streaming, which leaves the imprint of the CMB on the sky, leaving us with 2 thermal baths today. One at T nu naught. Sorry, let me just move this out the way of my screen. I think I can hide it. Sorry, yeah. One at a temperature which we're going to call T nu naught, which is the cosmic neutrino background, and one at TCMB, which is the cosmic microwave background, which we've already measured and studied quite well. So what can we say about the CNUB today? So based on this entropy conservation that I already mentioned, we can relate the temperature of the CMB to neutrinos, related by this 4/11 to 1/3 factor. We go ahead and we plug in the temperature of the CMB, which we've measured, And we find that relic neutrinos today exist at a temperature of about 0.168 millielectron volts. Now, importantly, this means that at least 2 out of 3 of the relic neutrino states have to be non-relativistic. We know that the lightest neutrino can be massless, but we also know the minimum masses of the 2 non-massive neutrino states from oscillation experiments. So if we set the lightest one to be massless, the other 2 have to have a mass which are equal to the square root of the mass splittings that we've measured. One of them is about 8 millielectron volts, and the other one's about 50 millielectron volts. So at least 2 neutrino states have to be non-relativistic today. And that's quite important for the cosmic neutrino background in some regards. We expect that they follow a Fermi-Dirac distribution, so that's just the equilibrium distribution redshifted, with a number density of about 56 per cubic centimeter per degree of freedom. In total, there are 6 degrees of freedom. There are 3 mass eigenstates, and there are neutrinos and antineutrinos, and only one of the helicity states is populated. The left helicity state for neutrinos, and the right helicity states for antineutrinos. If anybody's interested at the end, by all means, I'm happy to explain it. But however, and this comes down to what I said at the start of the talk, it may be different from this. The cosmic neutrino background may be different from this picture that I've given so far. For example, it might be overdense. You could have neutrino clustering, which can increase this number density. You could also have, say, dark matter, which decays to neutrinos and increases the number density and changes the temperature profile. Or, on the other hand, neutrinos themselves could be unstable, and I don't think there are any bounds that forbid them to be unstable on cosmological timescales, which means that the cosmic neutrino background might be diminished or might not even be there at all today. Just to sort of summarize what I've shown, or at least to compare them to other sources of neutrinos, I've got this nice little plot here. So on the right-hand side in black, we've got the solar, I don't know if you can see my cursor. We've got the solar radioactive spectrum. So these are the ones that come from nuclear processes in black. These are already reasonably well measured. We've got the ones from thermal processes, solar thermal processes like plasma decay in orange, and then in blue we've got the cosmic neutrino background. And what you can already see is that the cosmic neutrino background completely dwarfs these other 2 fluxes. So there are a lot of relic neutrinos. Unfortunately, what I also show on this plot are the thresholds for existing neutrino experiments. So radiochemical experiments with gallium and chlorine and boraxino, which is currently the lowest energy or the lowest threshold neutrino detector, at least to my knowledge, in the present day, which has a threshold of about 200 keV or so. And you can probably see that there's absolutely no way that these can detect the cosmic neutrino background. So if we want to see the CNUB, we have to seriously rethink neutrino detection, which is what I'm going to move on to next and talk about for the rest of the session. So the question is, how do we actually go about seeing the CNUB? We can't use techniques that we use for other neutrinos. We have to completely rethink things. Okay, so very briefly, we have 2 issues, right? 2 issues we've identified so far. The first one is the threshold. You need to get the relic neutrinos to interact in the first place. And then the second issue is the event rate. Neutrinos are, of course, neutrinos. Even if you can get them to interact in the first place, they typically have a low scattering rate or a lower whatever process they take part in usually proceeds at a slow rate. So you need to get a decent event rate if you want to get decent statistics. And this is made even worse by relic neutrinos because of how cold they are, right? I already said these things are non-relativistic. These event rates are even smaller for relic neutrinos than they are for other higher energy neutrinos. So how do we get past these issues? So on the threshold frontier, we can either look for a thresholdless process. This is something where any energy of neutrino can take part. Or alternatively, we can find some way to overcome a threshold by, say, giving some center of mass energy to the system and then bridging some threshold. On the event rate frontier, there are 2 things that we can do. We can either use a huge number of targets. This is, of course, the naivest approach. If I have an event rate that's, say, 1 event per 10 years per target, and I want an event per year, I can just use 10 targets, for example, right? And then I get 1 event per year. In the case of relic neutrinos, you'd need a huge amount of targets, but point is you use more targets, you get a bigger event rate. Alternatively, we can be a bit smarter and we can try and find a process with a bigger cross-section or with a bigger rate. And the things I'm going to show you today use some sort of combination of these things. Some of them use thresholdless processes, some of them use big number of targets, and so on and so forth. So the first idea I'd like to go through is the Ptolemy proposal. So this is based on a process proposed by Weinberg back in 1962, as all good things in physics are, where you take some neutrino from the CNUB, you capture it on a tritium atom, which gives an electron in the final state and a helium-3 ion. And the idea is that you measure the energy of this electron with extreme precision, which I'll show you in just a second exactly how that works. Importantly, this process has got no threshold whatsoever. So because tritium is a natural beta decayer, so you can move this neutrino to the right-hand side and have a beta decay process, you can capture a neutrino of any energy, which is very, very nice. And what's nice particularly about tritium is it's already pretty well understood from neutrino mass experiments. So we've been doing this kind of experiment for a very long time. So the Catherine experiment, which people may well be familiar with, which aims to measure the neutrino mass, uses tritium. When we've been doing this with neutrino mass experiments, like I say, for a very long time. So the energy release in a tritium beta decay is very well measured at this point, and it's also very small. So when you're trying to measure this electron energy with a very high precision, the sort of relative energy resolution you need is much smaller than if you had a very large threshold for a beta decay, or a large energy release in a beta decay. So let's just try and clarify what I mean by, or rather, what you actually want to look for at Ptolemy. So on this plot, I show 18.6 keV, the energy release in the tritium beta decay. And then to the left of that line, we've got the energy spectrum of the beta decay electrons. Now, in the box in the top right, very, very near to the endpoint, or very near to this 18.6 keV, we've got the endpoint of the beta decay spectrum. This corresponds to the electrons which are emitted with the maximum energy, which in turn corresponds to the point at which the neutrinos are emitted at rest. So by measuring the difference between this 18.6 keV and this beta decay endpoint, you can effectively measure the neutrino mass. These things will be separated by one neutrino mass, and this is what's employed at neutrino mass experiments. Now, on the other hand, at Ptolemy, you want to capture a neutrino in the initial state. So all of this 18.6 keV from the tritium beta decay, as it were, plus the energy of the incident neutrino is given to the outgoing electron. So you end up with peaks beyond this 18.6 keV by one neutrino mass, corresponding to a neutrino capture, which means these peaks are separated from the beta decay endpoint by two neutrino masses. So what you want to do effectively is look for these peaks beyond the beta decay endpoint, and you have some sort of evidence for the cosmic neutrino background. So what's the cross-section for this process? It works out to be something like 10 to the minus 45 centimeters squared. Is this a big or is this a small number? It turns out to be very, very small. So for reference, a typical electromagnetic cross-section, let's say the LHC, has a cross-section of about 10 to the minus 25. So this is 20 orders of magnitude smaller. We really need to use a huge number of targets to get this to work. Ptolemy planned to use 100 grams of tritium, which gives them an event rate of about 4 per year. Very nice. And this event rate is expected to be doubled for Majorana neutrinos. Why would it be doubled for Majorana neutrinos? Well, for Dirac neutrinos, you're only sensitive to the neutrino flux, the left helicity neutrino flux. You also have an additional right helicity anti-neutrino flux. However, those can't be captured in this inverse beta decay process. However, if you have Majorana neutrinos, of course, you can't distinguish between these right helicity antineutrinos and right helicity neutrinos, and you can capture them as well. Now, in practice, can you actually use this experiment to say that the neutrinos are Dirac or Majorana? Very likely no, because in order to see a factor of 2 in such a small event rate, when you have so many other systematics at play and maybe some other sources of a factor of 2. So, for example, if you have more neutrinos than you expect, or some sort of overdensity, you could get this factor of 2 from there as well. So to sort of concretely say that you had Dirac or Majorana neutrinos in this experiment is almost impossible, but in practice, or rather in theory, yes, you can say something about their nature. Okay, so what's the catch, right? If Ptolemy is so good, you got these peaks beyond the endpoint, and you got 4 events per year. Why haven't we built this thing yet, and why haven't we seen the cosmic neutrino background? Well, there are 2 main reasons. The first one is that you need incredible energy resolution in order to actually see the signal, right? So remember I said that these peaks were displaced from the endpoint by 2 neutrino masses. It means you need an energy resolution of less than twice the neutrino mass. Which is an incredible challenge. If we already had devices capable of resolving such small energies, or at least neutrino energies, we would have measured the neutrino mass by now. The second issue, and perhaps the more worrying one, it turns out, is actually getting hold of and storing this 100 grams of tritium, and more importantly, keeping it active. So by active, I mean you need to be able to measure the energy of all of the electrons that are emitted from these 100 grams of tritium at any one time. For reference, Catherine, which is the biggest experiment using a very similar principle currently, only uses about 300 micrograms of tritium at any one time. So Ptolemy, in theory, needs to scale this thing up by about a factor of 1 million. And as we'll see, this is quite a challenge. So what have Ptolemy said about these two issues, these are two main issues, what do they propose to do? So they suppose that they can get some energy resolution of about 50 milli-electron volts or so. The way in which they propose to do this is using this cyclotron radiation, which is the way in which future neutrino mass experiments propose to actually measure the neutrino mass. It's still very much an up-and-coming idea, but it certainly seems promising. And there are experiments and prototypes being built that use this idea. We know that the heaviest neutrino mass, even if the lightest neutrino is massless, the heaviest neutrino has to be at least 50 milli-electron volts. So this condition of the energy resolution being less than twice the heaviest neutrino mass should always be met. So Ptolemy should always see something. They should always be able to at least resolve the heaviest neutrino, the peak in this spectrum that I showed you due to the heaviest neutrino state. The second issue, and like I say, this is the one that's more concerning, is getting hold of this 100 grams of tritium. And there are several issues with this. So the first one is, of course, from an experimental point of view, hydrogen is not particularly nice to store. So hydrogen, the atoms of hydrogen are very, very small. They like to diffuse out of your container. So if you store this 100 grams of tritium, you leave it some time, half of it's going to have diffused out of your container, which is not great. Tritium, of course, is also unstable. So it has a half-life of about 10 to 20 years or so. So if you want to store this thing for 10 years, you have 100 grams to start with. You leave it for 10 years, you've only got 50 grams left, and your event rate's gone pretty much down to zero, right? Then there are more, I guess, political reasons. So tritium can also be used to make nuclear weapons. Governments don't like you to have so much of it. And then, like I say, the real issue is that you actually have to get hold of, you actually have to keep it active at any one time, which is, I guess, the main issue. So what have Ptolemy said on this frontier? Well, they've said that they can maybe use a graphene substrate. So the idea here is you have some substrate of graphene and you store the tritium, or you embed the tritium in the potential between the carbon atoms, such that they're all kept in place and kept active. Okay, very, very nice. However, there is a problem with this. And this was something that was only realized, I believe, some 4 or 5 years ago or so. It surprised me that it took so long for people to catch on to this, actually, given it seems like quite an obvious thing in hindsight. But in any case, there's an issue with the uncertainty principle here. So we know that the product of the uncertainty in the position of some particle multiplied by the uncertainty in its momentum has to be greater than or equal to h bar by 2. In natural units, 1/2, and if we saturate the equality, it's approximately equal to 1/2, which we can in turn translate into an uncertainty in the tritium velocity, right? By just rearranging the expression. This in turn leads to an uncertainty of the outgoing electron energy, which is what we're trying to measure, which is proportional to this velocity uncertainty. We can then go ahead and plug in the momentum of this electron at the endpoint, which we know, which turns out to depend on the threshold, the electron mass, or the tritium mass, and so on. If we suppose that the confining potential, so the interatom spacing in this graphene lattice, is about 0.1 angstroms or so, we end up with an electron energy uncertainty of about 480 milli-electron volts. Now, this is, I should say, just a crude estimate, back of the envelope. There are more precise estimates in the literature. By all means, go look for them. This is just one back of the envelope, just to sort of illustrate the point. But anyway, you end up with an uncertainty of about 480 milli-electron volts. And importantly, this is much, much larger than twice the heaviest neutrino mass. So Ptolemy is no longer guaranteed to see anything. And indeed, when the energy resolution is this bad, the actual sensitivity to the cosmic neutrino background becomes diminished by many, many orders of magnitude, 7, 8, 9. It really is quite bad. So Ptolemy is no longer guaranteed to see anything. So even though on paper it seems like a very nice idea, there are some serious experimental issues that they need to overcome before they can actually get this thing to work, which is why we should consider other proposals, which is what I would like to move on to next. But before I do so, what have Ptolemy said about this uncertainty principle issue, right? They have acknowledged that this issue exists since it was pointed out, and they have suggested some ideas. The main one the one that I at least understand best, is this idea with carbon nanotubes. So rather than using a completely flat substrate of graphene, they plan to instead use these carbon nanotubes, which allow the tritium to slide up and down in the Z direction, as it were. So the direction which is perpendicular to the substrate, as it were, which it turns out is the most confining direction. This in turn increases the uncertainty in their position and decreases the momentum uncertainty, which could potentially overcome this. However, now there are a lot of difficulties in actually getting 100 grams worth of nanotubes, and it's still not guaranteed that this would solve the issue. They also propose some other ideas, which, like I say, I have to be honest, I don't fully understand. There's a full paper on it. I think, hang on, this paper here is where they address the issues. This one from 2022. So if you want to go and look at them, by all means, go and visit that paper. But yeah, my understanding is that there's no clear solution to this issue at present. So we should be looking into other proposals, which is what I want to go into next. Next, I want to talk a little bit about the coherent scattering proposal. Okay, so coherent scattering. What is coherent scattering? It's where you take some neutrino, you scatter it on some target X. This is typically a neutral current interaction, which gives you the same target in the final state plus the neutrino, just with ever so slightly different energies. What makes it coherent is when the neutrino, the instant neutrino, has a wavelength which is of order the size of the target, or I guess more accurately, when the Q value or the momentum transfer, or 1 over the momentum transfer rather, is of order the size of the target. What's special about coherent scattering is that the neutrino sees a larger charge. This is just again a rough explanation of why you get enhanced event rates when you have coherent scattering. But more concretely, there's a bit more of an in-depth derivation you can do, but I won't do it here to save time. So back of the envelope, we know that an amplitude, a scattering amplitude, is proportional to the charge of the thing that you're scattering off of. And when the neutrino sees more than one target at any one time, because it has a larger wavelength, this charge is going to be proportional to the number of targets that the neutrino sees. This could be a number of protons or a number of neutrons or something along those lines, right? As a result, we get enhanced event rates. So any cross-section is going to be proportional to the amplitude squared, and the event rate is proportional to the cross-section. So rather than an incoherent scattering rate, which scales up the number of targets to the first power, a coherent scattering rate is going to scale something like the number of targets squared. Now, why is this very nice for relic neutrinos? Well, let's just consider coherent scattering on atomic nuclei. This is something that's been measured since, I think, 7 or 8 years ago or so by the Coherent collaboration, where they take some sort of mega electron volt neutrinos, which have wavelengths of order a few femtometers, and they scatter off of an atomic nucleus coherently, right? So they pick up some enhancement factor, which goes something like the number of nucleons squared. Very, very nice. In the case of relic neutrinos, however, this case is even more extreme. So they have momenta of order a few milli-electron volts, which means they instead have wavelengths of order a few millimeters, which is maybe the size of an ant or some sort of macroscopic object. Which means for sort of a few moles of atoms or targets or whatever you're scattering off of, you get a cross-section or a scattering rate which scales something like the Avogadro number squared rather than the Avogadro number to the first power. So you pick up something like a 10 to the 23 enhancement in your rate with relic neutrino coherent scattering, which is absolutely huge. So just to really sort of hammer this home, we can look at the naive estimate for a scattering rate for relic neutrinos. A neutral current scattering rate will go something like GF squared, the Fermi constant squared. This is a very small number, multiplied by the neutrino mass. This is a sort of energy scale in the process, multiplied by the neutrino temperature cubed. This just comes from the number density of the neutrinos, and this other part just comes from dimensional analysis. You plug in the numbers and you find that this is about 10 to the minus 39 events per year per target that you're scattering off of. This is absolutely tiny. So yeah, per mole of target, now you find that you get about 10 to the minus 16 events per year. So you could wait the age of the universe and you would never see one incoherent neutrino scattering event. However, when you take the coherence effects into account, you get an extra Avogadro number enhancement, and now you find that you have something like 10 to the 7 events per year, which is now very, very large. And you can go ahead and estimate for, say, a typical setup. There have been some papers, including one of my own, where we looked at maybe scattering gravitational wave detectors and also scattering say on a torsion balance, and you find that the typical scattering rate is something of order a few kilohertz, which is now very, very reasonable. But the question then is, why haven't we seen anything yet, right? If these things are scattering at a rate of kilohertz, why haven't we seen this process by accident, right? We should have seen this by now. And that turns out to have quite a simple answer. It's because relic neutrinos are very, very cold and light. So neutrinos, of course, are very, very light. They have a very small mass and they have a very small momentum in the case of relic neutrinos. So every time they scatter, they only transfer, on average, something of order a few milli-electron volts of momentum to the target, which is basically nothing. This is something you're never realistically ever going to see. However, it does give rise to a very small acceleration, and you can estimate how big this is for, say, again, something like a torsion balance, and you find that it comes out to be something like 10 to the minus 28 centimeter per second squared, depending on the neutrino mass. Now, what can we actually measure? What's the best acceleration we've ever seen? Something like 10 to the minus 15 centimeter per second squared in the tests of the weak equivalence principle. So with this coherent scattering idea, we're about 13 orders of magnitude off, which begs the question, right? Why have I wasted your time in showing this proposal? It's 13 orders of magnitude off. Well, as we'll see as we go later in this talk, all of the relic neutrino detection proposals are a very, a similar order of magnitude off. So this one is not anomalous in how bad it is, and if you take into account the fact that Tollum is very unlikely to work with its current setup and the energy resolution is as bad as it is, it's a very similar order of magnitude off. I think it's slightly better than this, but it's still very comparable. But what can we say about this potentially going forward? Well, there was a paper in the 90s or so that suggested they could build a torsion balance with a sensitivity of about 10 to the minus 23 centimeter per second squared, which in that case means we'd only be, 5 orders of magnitude off seeing the CNUB. The issue, however, I have with this paper is that it came out in the 90s and there have been no follow-ups to it since. And if this idea was buildable and was reasonable, surely somebody would have commented on it at the very least between now and then. So I don't want to dismiss it outright because it's a very technical paper and I'm definitely not an experimentalist, but I definitely have my doubts about it. So I would say naively use this 10 to the minus 15 centimeters centimeter per second squared as sort of the reference value to consider when talking about coherent scattering, which means we're about 13 orders of magnitude off. Okay, right. So next I want to move on to the Stodolsky effect. Yeah, normally this is where I'd ask questions, but I think we're having them at the end, so I will move straight on. Okay, right, so the Stodolsky effect. What is the Stodolsky effect? It's analogous to the Zeeman effect. So just to jog everybody's memory, the Zeeman effect is where you put some charged particles, typically a charged fermion in a magnetic field, and you observe some energy splitting between its two spin states proportional to the strength of the applied magnetic field. The Stodolsky effect is more or less the same thing. If I put something which interacts with neutrinos, again, something like an electron or a proton, in the cosmic neutrino background, I get some energy splitting between the spin up and spin down states proportional to any asymmetry in the cosmic neutrino background. That can either be the asymmetry between the number of neutrinos and antineutrinos or between the number of left and right helicity neutrinos, which turns out to actually be the same in the CNUB, at least in the standard scenario. And what's nice about the Stodolsky effect is it's the only effect which is linear in G Fermi, which means it's typically, you expect, going to be a slightly larger than some of these scattering processes that I've shown so far. Now, I put this little asterisk next to the star, next to the word only, because there were some proposals very early on that suggested there were other effects that were linear in GF. How these were later shown to be unlikely to exist purely because there needs to be some sort of spatial gradient in the CNUB in order to actually have these effects. And that's not expected to be there. However, more recently, there were some papers that came out a couple of years ago that suggested there may be some local effects which give rise to these spatial gradients. But then since then, there have also been some papers which have come out which have contested these claims. So it's a bit up in the air as to these other effects currently. So for now, we just consider the Stodolsky effect. It's the only effect linear in GF. And it looks a bit something like this. So if I have no asymmetry in the cosmic neutrino background and I have some fermion which interacts with neutrinos, its spin up and spin down states are going to have the same energy. However, if I have some asymmetry in the cosmic neutrino background, so some difference between the number of neutrinos and antineutrinos or between left and right helicity states, I develop some energy splitting, right? And this energy splitting is proportional to GF to the first power. Beta Earth, this is the relative velocity between the CNUB frame and the Earth reference frame. And the difference between the number of neutrinos and antineutrinos. Is this a big splitting? You're probably going to guess it's very, very small. It turns out it is. It's about 10 to the minus 38 electron volts multiplied by this asymmetry parameter, which can go between 0 and 1. 0, no asymmetry, 1, maximal asymmetry. To compare this with the Zeeman effect, for a 1 Tesla magnetic field, you would expect an energy splitting of something like 10 to the minus 4 electron volts. So this is 34 orders of magnitude smaller in the best case scenario. So there's absolutely no way you can see the Stodolsky effect with spectroscopic methods. So then the question is, how do we actually ever see this thing? And yeah, there's an effect which depends on helicity asymmetry, which we'll come on to a little bit more later on. So how do we see the Stodolsky effect? We can't use spectroscopic methods. Well, it turns out that there are two observables and they come down to the same effect, which is a spin precession. So because we now have some spin dependence to our energy levels, our Hamiltonian will pick up a spin-dependent component, which means it no longer commutes with all of the different spin operators, which leads in turn to some sort of spin precession, right? Some time-dependent spin for the the spins which are perpendicular or orthogonal to the cosmic neutrino background wind. This in turn gives rise to two observables. The first is a torque. So if I have something like a ferromagnet where all of the spins are fixed in place and they're attempting to process about the cosmic neutrino wind, the whole object will experience a torque. It will feel a torque which is proportional to the energy splitting. This in turn gives rise to a very small acceleration of the object. We've seen this before, 10 to the minus 27 centimeter per second squared, again multiplied by this asymmetry parameter, which we could maybe measure with some sort of small torsion balance. For reference, we've already seen 10 to the minus 15, and with this superconducting torsion balance proposal, maybe we can go to 10 to the minus 23. So Stodolsky effect is, assuming maximal asymmetry, one order of magnitude better than coherent scattering. If the asymmetry is very small, however, it could be worse, at least with this proposal. The second observable, which I think is more promising, is looking for a time-dependent magnetization of your target. So now suppose I have some target with all the spins aligned along one direction. It's also going to generate a magnetic field of its own, right? And if these spins are allowed to precess, so they're not fixed in place as they are in, say, a ferromagnet, this magnetic field will change its direction in time. So just to sort of, how would I best describe it? And to show exactly how this idea works, I've got this little plot which I'm going to try and build up to try and explain the experimental setup for the magnetization with the Stodolsky effect. Okay, so suppose I've got some target represented by this blue circle, where initially all of its spins are unpolarized. So there's no net magnetic field being generated by this target. I apply some very strong external magnetic field to my target, such that I polarize all of the spins in the target and they all point along one direction, which is parallel to the applied magnetic field. Recall, of course, I've also got the cosmic neutrino background wind passing by. Ideally, this should be exactly perpendicular to the applied magnetic field. However, it doesn't have to be, and because of course you don't know the direction of the neutrino wind necessarily. So long as it's not exactly parallel to the applied magnetic field, there's no problem here. And you can always get around this by, say, rotating your apparatus by 90 degrees between two, say, measuring periods or something. That would completely get past this issue. So let's just assume for our purposes that it's perpendicular. Now what we want to go ahead and do is, and this thing acts something like an extra magnetic field. That's how you should think of it. This neutrino wind acts very similar to a very weak magnetic field. What we then want to go ahead and do is turn down the strength of this applied magnetic field, this external magnetic field that we apply in the lab. This now sort of frees up the spins in the target and it lets them process around the neutrino wind, like so. And then what will happen is they will also be kicked out of alignment with the applied magnetic field, so they should also start processing around that at the same time. As a result, we'll end up with two magnetic fields. We'll end up with a component which is parallel to the applied magnetic field, and we'll end up with a component which is perpendicular to the applied magnetic field. And this perpendicular component would never have appeared if we didn't have the cosmic neutrino background wind, right? Because otherwise it wouldn't have been kicked out of alignment with the applied magnetic field, and it would never have started processing around it. And the idea is then that you measure this very small perpendicular magnetic field with something like a squid magnetometer. And the signal looks a bit something like this. It's quite nice, it turns out. It has a very nice time dependence where it reaches its maximum at sort of 1 over the Lambda frequency, right? It processes at the Lambda frequency about this applied magnetic field. So what you do is you look for this maxima in periods of 1 over the Lambda frequency. Okay, so how big is this perpendicular magnetic field expected to be? It's about 10 to the minus 25 Tesla multiplied by this asymmetry parameter. For reference, we are sensitive to something like 10 to the minus 16 Tesla or so, which means that we're about 9 orders of magnitude off. However, remember I mentioned that we had this helicity asymmetry term. This is expected to be about 3 orders of magnitude larger or so, in which case we're only about 6 orders of magnitude off of measuring this thing, which is now significantly better than coherent scattering. However, we have to say something about this asymmetry because, of course, if we just assume it's equal to 1, we're probably going to make a mistake. So from BBN, we know that this asymmetry has to be less than, so Big Bang nucleosynthesis, we know that this asymmetry parameter, which should be approximately equal to the helicity asymmetry parameter, has to be less than equal to about 10 to the minus 2, which in turn means that the perpendicular magnetic field, taking into account the helicity asymmetry term, which is 3 orders of magnitude bigger, has to be less than or equal to about 10 to the minus 24 Tesla. And again, for reference, we're sensitive about 10 to the minus 16. So in the best case scenario, we're probably about 8 orders of magnitude off with the Studolsky effect. But we are still significantly better than coherent scattering with this idea, which is one reason I find it quite interesting. And it's also sensitive to other things like whether you have an asymmetry in your background. And it can also reasonably well distinguish between Dirac and Majorana neutrinos, as I'll come on to a little bit later. The last proposal I want to go through is the accelerator proposal. This is the first thing I ever worked on in my career as a physicist. This was my first paper when I very first started my PhD, so it holds a bit of a special place to me. It's a very strange idea, as hopefully you'll see in a minute. So what I want to do to start with is try and talk you through the ideas that led us to arrive there. So when I started my PhD, my supervisor and I, Martin Bauer, we were looking at the Ptolemy proposal to detect the CMB, and we noticed in the cross section that there was this dependence on the electron energy, right? It goes something like the electron energy squared, and we figured if we put the tritium atoms on a beam, maybe we can increase the energy of the electron sufficiently in the final state, such that the cross section is bigger, and we can reduce the tritium requirements, because that was the biggest issue for actually building the Ptolemy experiment. However, we very quickly realized that this doesn't really work. So why doesn't this work? Again, it maybe should be fairly obvious, but just to spell it out, the neutrino energy in the rest frame of the tritium, which is on a beam, goes something like the neutrino mass over the tritium mass multiplied by the beam energy. And we want that this neutrino mass is of order the electron mass, such that we get some enhancement in this cross section. So you can go ahead and solve this equation with E nu equal to the electron mass, and you find that the beam energy needs to be greater than something like the tritium mass over the neutrino mass multiplied by the electron mass, which works out to typically be of order a few PeV, a few peta electron volts, about 1,000 times more energetic than the LHC. So you can see that this is an absolute nightmare. You don't want to do this, and if you build something this big, even at 1 PeV, for example, you only gain, say, 1 order of magnitude in your cross section. So you still need to put 10 grams of tritium on your beam, which is not really worth it. If you wanted to increase it by a significant amount, you'd have to go up to ridiculous energies that are just completely infeasible. But we figured if we were going to be so crazy as to consider building a beam of this sort of energy, or of this sort of scale at least, we might as well start at least considering thresholded processes, right? So processes now where the neutrino needs a minimum energy to actually take part. And if we did, we realized we could actually start exploiting resonances, which I've spelt wrong up here. Yeah, the idea here is if you tune the beam energy so that you precisely hit a resonance, you can get quite a large cross section. So take, for example, this is not one you could put on a beam, but an example of a neutrino resonance. This is Z resonance. So if I have some ultra high energy neutrino, which can set off the cosmic neutrino background, this is indeed a proposal to look for the C nu B. At the Z resonance, so you produce the Z boson directly on shell, you have an absolutely huge cross section compared to the non-resonant cross section. It goes something like 1 over mz squared, which is proportional to gf to the first power. So by using a resonance, we've massively increased the cross section. Of course, we can't use, like I say, this process on a beam. We can't put these neutrinos on a beam to hit this resonance. So we need to look for different resonances. And there were 2 that we identified. The first one is one that we're going to call the resonant electron capture process, where you take some parent state P with an electron bound around it. So this is something that might look hydrogenic, or maybe it has more than one electron, but simplest case, it looks something hydrogenic. You put this thing on a beam, and you scatter it off of some relic neutrino from the cosmic neutrino background to give you some daughter state D. This is something that looks very similar to a 2-to-1 process, because this thing is bound, and it's a resonance. The other process is this resonant bound beta decay process, where you have some parent state P on your beam, you capture some electron neutrino from your background, giving you some daughter state D, and an outgoing electron, which is captured by one of the electron orbitals of this daughter state D, and is end up bound. So again, this looks something like a 2-to-1 process, and it's a resonance. Now, these processes have absolutely huge cross sections when you're directly on resonance. They go something like 1 over q squared, multiplied by the branching ratio for the daughter state to decay back to the parent state. This is typically order 1, this branching ratio. So you go ahead and you plug in the numbers for, say, a 1 kV gap, which is fairly reasonable, and you find that this is something like 10 to the minus 15 centimeters squared. So for reference, I already mentioned this earlier, but just to remind everyone, this typical electromagnetic cross-section is about 10 to the minus 25 centimeters squared. So this is 10 orders of magnitude bigger than a typical electromagnetic cross-section. So this really is quite huge. However, there are some issues, as there are with all of these proposals. So let's just look at these processes in a bit more detail. So for the resonant electron capture process, you take some parent state P, you resonantly electron capture to some daughter state D. And the idea is that you would effectively run this ion beam of parent states through the CNUB for some given amount of time. You would strip the electrons off, and then you would count the number of daughter states. Seems easy enough. However, this daughter state is itself unstable. Parent state P is stable, daughter state D is unstable. And it can decay back to the parent state, or it can, through bound beta decay, or it can continuously beta decay to some parent state P+. Which means that eventually what happens is you build up enough of a number of daughter states on your on your beam that the decay rate back to parent states is equal to the number of neutrino captures produced in the daughter state. So your signal eventually stagnates and you don't get any you could run this experiment effectively forever and you're never going to see any more signal than if you ran it for, say, 10 minutes, which is not particularly promising. And there's a similar problem for the resonant bound beta decay process, where your daughter state can electron capture back to the parent state. And it ends up looking a bit something like this. So on the y-axis, we've got the beam conversion fraction, which is the number of daughter states you expect to see on your beam as a function of x, which is the normalized experimental runtime. So this is the actual runtime, the real-world runtime, divided by the daughter state lifetime. And you see at very small values of x, so when you're well below the daughter lifetime, your signal increases over time. Fantastic. But as soon as you hit the daughter lifetime, the daughter states start decaying back to p states, and your signal effectively stagnates and you reach equilibrium. And this is obviously not good from an experimental point of view, right? You actually want to see this thing. So how can we overcome this? It turns out that there are three-state systems. We found these by accident, and they're very, very nice. So a three-state system has a final state that differs from the initial state, and it looks a bit something like this. So take the resonant electron capture process. Now our daughter state can bound beta decay back to the parent state or continuously beta decay to the P+ state, same as it could before. However, it can now also electron capture a second time. This is without capturing a neutrino, just a singular normal electron capture, no neutrino involved, to some final state F, which itself is stable and is different from the parent state P. And in the same way with the resonant bound beta decay process, the daughter state here can bound beta decay a second time to some F state. And the idea then would be that you count these F states after you've run your experiment for a very long time. And in theory, given enough time, all of your P states should end up in F states, right? Because the neutrinos will force them into the D state, and then there'll be some probability that they decay to the F state or to the P state. And if they decay back to the P state, eventually they'll end up back in the D state. But if they end up in the F state, they will stay there indefinitely. Of course, they can also be lost from the beam if they end up in these plus states, which have a slightly different charge mass ratio, but these processes tend to be quite small. So for a three-state system, you end up with something that looks a bit like this. So now x equals 0. I should say the solid line is the number of f states on the beam, and the dotted line is the number of f states plus d states on the beam at any one time. Now x equals 1, what you see is the signal no longer stagnates, but it carries on increasing indefinitely, as all of these daughter states eventually end up in the f states, which is very, very nice. So what can we actually do with this kind of experiment? So I will give you an example of a two-state system. I know I said they were bad, but it turns out this one's actually not so bad. It doesn't actually reach this equilibrium point in 1 year or reasonable runtime. I think the lifetime of this terbium is much, much longer than, say, a year, for example. In any case, an example of this 157 gadolinium system, which can resonantly bound beta decay to 157 terbium. It has a threshold of about 10 kV or so. Which means you need a beam energy of about 100 TeV in order to get this thing to work. Now, already I can see people are thinking, oh, this is not particularly great. I don't want to build a 100 TeV accelerator for something like this. And I appreciate that that's a really crazy idea. But when we go ahead and we build this 100 TeV accelerator, what do we get? How many daughter states do we expect to see on our beam after 1 year? 10 to the minus 12. Okay, now probably there are people in the audience saying, go and get a new job. You're wasting my time. However, it's not a complete waste of time. So what I want to highlight is that in general, the number of daughter states you expect to see on your beam after any given runtime goes something like 1 over the threshold to the 7th power. So there's a q squared factor which comes from this resonant cross section, and then there's a q to the 5th power which comes from the number of parent states that you can actually put on your beam at any one time. So because of the amount of radiation that these parent states emit, you can only put so many of them on the beam before you end up damaging your detector. And we did a rough estimate of how many you can potentially put on, and we find that it goes like 1 over q to the 5th power. power. So in general, the number of daughter states you expect to see after some runtime goes like 1 over q to the 7th power, which implies that if we find something with a threshold of about 0.1 keV or so, this number then becomes order 1. This then goes up to, say, a factor of 100. This goes up to something like 100, and potentially we can actually observe this effect. Now, finding something with a threshold of 0.1 keV, it turns out it's very challenging. The smallest thresholds we were able to find are of order, say, 1 to 2 keV, but we did have some ideas as to how you can manufacture something with a very small gap. So, for example, you can use excited states on your beam instead of ground states, which leads to experimental challenges of its own, but lets you tune the Q value. And there's also no reason in particular why you have to use the two processes that we consider, right? So I've presented to you these resonant band beta decay, resonant electron capture processes. There's no reason why you have to use those. This idea works in general for any resonant process that you can put on a beam. So, for example, you could consider putting muons on the beam, capturing a neutrino, and producing pions in the final state, right? Instead of producing a different atomic nucleus. Now, of course, that's a terrible idea because the gap in that case is about 30 mega electron volts, right? Way bigger than this. But somebody much smarter than me could potentially come up with something better than an atomic system or a nuclear system, and maybe this could be doable. And I should also add, right, whenever you decrease the Q value, you also reduce the beam energy requirement. So every order of magnitude you go down in your Q value, you go down 1 order of magnitude in your beam energy requirement. So if a Q equals 0.1 keV, you only need a 1 TeV beam, which is a lot more reasonable with the sort of technology that we currently have. Okay, so the last thing I want to go through today, I think I've got about 10, 15 minutes left. There's plenty of time, actually, are the constraints on the cosmic neutrino background. So we've seen so far that the detection feasibility, so the sensitivity of all of these experiments is largely determined by 3 parameters. The first is the neutrino overdensity or the neutrino number density. So this is just the ratio of the number of neutrinos to the number of neutrinos that we expect from cosmology. In the standard model, this is obviously just 1. But it doesn't have to be 1, right? There are you could have clustering or so on, like I've already mentioned at the start. The neutrino mass, this plays a key role, and the neutrino temperature, which affects the neutrino momentum. So if we go ahead and we map out the allowed parameter space and we see which regions are accessible for the CNUB, i.e. which ones are allowed, maybe we can overlay on top of this our sensitivities of all these experiments and see which one is the best detection proposal. So we're going to start with the constraints. These are the present day constraints on the cosmic neutrino background. These aren't ones necessarily from the early universe. The neutrino mass ones are, but in general, these aren't early universe constraints on the CNUB. Because they might not necessarily hold in the present day for the reasons I mentioned at the start of the talk. So going from top to bottom first, we have constraints on the overdensity. So again, this is the number of neutrinos relative to the expected number of neutrinos set by neutrino mass experiments. The bound currently sits, the best one currently sits about 10 to the 11 from Katrin. And the reason Katrin can set bounds on the cosmic neutrino background over density is because it works in exactly the same way as, say, the Ptolemy proposal plans to work, right? I already showed you this plot at the start where you get this beta decay spectrum and the kind of thing you expect to see at Katrin. Katrin can, in the same way as Ptolemy, look for these peaks beyond the endpoint of the beta decay spectrum. It just doesn't have a good enough energy resolution and enough tritium to actually resolve anything. So it can only set constraints on the cosmic neutrino background. And this dotted black line is the proposed reach of Katrin. By the time they've analyzed all of their data, they expect to be able to set a bound on the cosmic neutrino background over density of about 10 to the 10 or so. Then going from right to left, we've got constraints on the neutrino mass. We've got Katrin sits at about 0.8 electron volts, which more recently has been updated to about 0.45 electron volts, which sits further to the left. Then in green, we've got the bound on the sum of the neutrino masses from cosmology. This bound that I've shown here is from Planck. There's a more recent bound from DESI, which is slightly stronger, about 0.07 electron volts on the sum of the masses. And then if we allow neutrinos to be unstable, so this is for stable neutrinos, if we allow neutrinos to be unstable, the bound then gets relaxed to about 1 electron volts on the sum of the masses. But if they're Majorana neutrinos and unstable, there's a slightly stronger bound that exists from Camland, coming from neutrinos double beta decay. And then in blue, the strongest bound by far, the one I've been avoiding so far, is from the exclusion principle. So of course neutrinos are fermions, and we can only fit so many of them into the galaxy before they start violating spin statistics. And it turns out for the cosmic neutrino background, because they're so cold, that they're almost approaching that degenerate limit already. So more or less, the exclusion principle limits the cosmic neutrino background to have an order 1 overdensity for most of the parameter space. So in this white region is pretty much the only region that's allowed, that cosmic neutrinos are allowed to live in. So on top of that, now I want to overlay the sensitivity of the experiments that I've discussed so far. So in orange, we've got the Ptolemy proposal. I want to add as well, by the way, so the solid lines here are for Dirac neutrinos and the dotted lines are for Majorana neutrinos. So the Ptolemy proposal is very, very sensitive down to its energy resolution of about 0.05 electron volts or so, at which point the sensitivity becomes very, very bad. But above this sensitivity, it's pretty much sensitive to order 1 overdensities. Now, of course, I did say that Ptolemy was not particularly great in the fact that they have this uncertainty principle issue. If you reduce the energy resolution, or you increase the energy resolution to half an electron volt or so, this point here where the order 1 sensitivity begins and the bad sensitivity starts, or whatever, this I don't know what you call it, like a knee here. This moves to the right significantly. It moves to about half an electron volt or so. And also the whole plot moves upwards. So the rather than be sort of 10 to the 5 or 10 to the 6 in the bad region, the Ptolemy proposal is now only sensitive to something like 10 to the 8, 10 to the 9 overdensity in this region. So it becomes significantly worse. And moving on, we've got the Studolsky effect, which is sensitive to overdensities of about 10 to the 10 with a torsion balance. But pretty much the entirety of the mass parameter space. With the magnetometer, this is about 3 orders of magnitude better, something like 10 to the 7 or so, which is quite a lot nicer. But what you may have noticed is that at very high masses, the Studolsky effect seems to completely lose sensitivity. Right? The Majorana line basically goes off to 0, and the Dirac line gets really, really bad, and then it cuts off and reaches this constant value. So the question is, why does that happen, right? You probably ask why that happens. So this is to do with the helicity asymmetry term that I mentioned earlier. So if you have some asymmetry in the cosmic neutrino background reference frame, so the cosmic neutrino background reference frame is not necessarily expected to align with the Earth reference frame. There's no reason a priori why it should. So the CMB frame, for example, doesn't align with the Earth reference frame. There's a slight dipole there. You expect the similar thing to be true for the cosmic neutrino background. If you have a helicity asymmetry in this cosmic neutrino background frame, when you make the frame transformation between the CNUB frame and the Earth reference frame, if the Earth is traveling faster locally than the average velocity of relic neutrinos, this helicity asymmetry vanishes. It gets washed out, which means for Majorana neutrinos, where only this helicity asymmetry term exists, the effect goes to 0. Whereas for Dirac neutrinos, only the neutrino-antineutrino asymmetry term survives, which is about 10 to the 3 smaller, giving rise to this constant line here. Then the coherent scattering proposal is more or less the same for the entirety of the mass range. It gets slightly more sensitive as you go to higher masses, purely because you transfer slightly more momentum per scattering event. And then finally, we've got the accelerator experiment, which is 10 to the 15 orders of magnitude off. This is for the gadolinium system that I mentioned on the last couple of slides. It's very, very bad at low neutrino masses because you can't put many states on your beam before you end up ruining your experiment. As you go to larger neutrino masses, however, you reduce your beam energy requirements, you increase your number of targets on your beam, and you get a significantly better effect. And in fact, it becomes the second most sensitive experiment of very large neutrino masses. Unfortunately, these neutrino mass ranges are excluded, which is not particularly good. However, like I said earlier, if you reduce the threshold by, say, 1 order of magnitude, you end up instead at this dot-dashed green line down here, where the accelerator experiment, say, is already the second best experiment and potentially even better than Ptolemy in these very large masses. And if you increased it by 2 or decreased the threshold by 2 orders of magnitude, you would now gain another 7, and it would put it above Ptolemy pretty much everywhere. So the accelerator experiment, whilst it seems bad on paper, if somebody smarter than me goes ahead and finds a system where the threshold is very, very small, potentially it could become the most sensitive experiment out there. And then just showing the same plot now in terms of the neutrino temperature. So rather than as a function of the lightest neutrino mass, now as a function of the neutrino temperature. So this is the temperature divided by the expected relic neutrino temperature. So again, the standard model sits at this point here with the ratio equal to 1. We end up with this plot here. So Ptolemy is more or less the same. When you're above the energy resolution, you have good sensitivity. Below it, you have terrible sensitivity. Studolsky effect more or less the same. When the neutrinos become very, very cold or very slow, the helicity asymmetry gets washed out, which is what this very interesting structure here is. The accelerator experiment, very much the same. High energies, lower beam energy required, more targets, so on and so forth, better sensitivity. But the main differences are the coherent scattering and the exclusion principle. So one by one, coherent scattering becomes more sensitive because when you go to very low temperatures, your neutrino momentum gets smaller. And as a result, it has a larger wavelength. You can scatter off of larger targets coherently, and your sensitivity goes up hugely. It goes up, I think, about 3 orders of magnitude per order of magnitude in the temperature that you go down. So if the relic neutrinos are significantly colder than we expect them to be, then coherent scattering could be very, very sensitive to them. And then the exclusion principle is also itself sensitive to the temperature. So if neutrinos are hotter, they have smaller wavelengths, and so you can cram more of them into your galaxy before you run into the exclusion principle bound. And this thing goes something like T cubed. So if neutrinos are very, very hot, the overdensity is allowed to be much larger than it is if neutrinos are very, very cold. So all of these regions are pretty much excluded. All of these regions to the right are potentially allowed. So the cosmic neutrino background could live in this little triangle here. And that's it. So very quickly, just to summarize, the cosmic microwave background is currently the furthest that we can look back through time. And detecting the CNUB as a result could reveal a wealth of new physics. So since the CNUB predates BBN, you could gain some insight into Big Bang nucleosynthesis. You could also gain insight into potentially some dark matter which might interact with neutrinos, leading to things like neutrino decay or something along those lines. There's a lot of new physics you could search for with the CNUB. And again, people want me to talk a bit more about that at some point. I could. There's a lot of exciting stuff you can do with the CNUB. Unfortunately, the detection is made difficult by the neutrino properties. Hopefully, I've managed to convince you that it's a difficult thing to do. And like I say, if you look at this plot, all of these proposals are, especially if you move Ptolemy up based on the bad energy resolution from the uncertainty principle, all of these things are many, many orders of magnitude off. So it's a very, very difficult thing to do. But hopefully, I've managed to convince you at the very least that there are a lot of exciting proposals to detect the CNUB. And that's it. Thank you very much. Are there any questions?
Okay, thank you very much for the very nice, comprehensive talk. So before going into the questions from YouTube, I'd like to ask the other organizers if they have any questions.
Yeah, I have a question for Jack. Yeah, when you were mentioning all these hard problems with detecting the cosmic neutrino background, is it possible also to use the same setups that, for instance, dark matter detectors for direct detection? Let's say, because I remember that, for instance, for other type of energies or neutrinos, they are trying to establish some detection with the kind of coherent using xenon or LC. So for this case, could be complementary search or something like that.
It depends. So there are these searches. If you're looking at say WIMP searches, so these like big xenon experiments and so on and so forth, they have, if you ask me, they have zero chance of ever seeing anything from the cosmic neutrino background, purely because the recoil from any scattering event would be so low, you would never see anything, right? So I think of these WIMP experiments, they're looking for, MeV to GeV sort of range, dark matter, or heavier even, right? Where the recoil is big. Relic neutrinos basically transfer zero momentum with every scattering event, so you're never going to see that kind of experiment. However, the question of could dark matter detectors see relic neutrinos as a sort of broader topic, potentially, right? So the way I like to think, and the reason I also work on light dark matter searches is because one way in which you can think of the cosmic neutrino background is as light dark matter, where we know the spin, we know the couplings, and we roughly know the mass. So if you set up some light dark matter, some detector for very light dark matter, which is a lot of what these quantum sensors do nowadays, this is the sort of thing I'm very interested in, you might actually be sensitive to the cosmic neutrino background at those. It turns out that in general, something I found in my work on this, the cosmic neutrino background is actually harder to see than a lot of dark matter models. It actually ends up that the dark matter would probably be a background to relic neutrinos at a lot of these things. Obviously, it depends what the dark matter is. Which should tell you how hard relic neutrino searches are, right? If you're talking about dark matter being a background to your search, then you really are running into problems. But in theory, yes, you can potentially look for relic neutrinos at some dark matter searches, but just not the big WIMP searches with xenon and these kind of things. You've got no hope there.
Thanks. Just another question before.
Yeah, go ahead, go ahead.
I know that there are many in the chat in YouTube. So the other question is related with the. I mean, you were talking mostly about the standard picture of neutrinos, let's say. But
Yeah, the standard cosmological model. Yeah, mostly. Yeah.
yeah, but this type of searches also. I mean, if you have a kind of cosmological history that gives you more cosmic background neutrinos than the standard picture, it could be also
Yeah,
search for non-standard scenarios for cosmology. I mean, to test the cosmological
yeah, of course.
from
Yeah,
now.
of course. I mean, but there are some issues with that. That's the problem. So the main one that you run into issues with is the exclusion principle, right? So whatever theory you come up with, it can't violate the exclusion principle. You can't put more neutrinos in the galaxy than are allowed by spin statistics. It doesn't matter what you do. So this Pauli exclusion principle bound, will just kill you. If you come up with a model where you have more neutrinos than this, you basically can rule it out based on the exclusion principle. Now, you can get around the exclusion principle bound in one way. So this bound is based on the escape velocity of the galaxy, which is purely gravitational. If neutrinos have new long-range forces interactions, you can change their escape velocity and make it larger. And if you do that, then you can weaken the Pauli exclusion principle, and then you can have a significant overdensity. But that's basically the only way, because other than that, you effectively have no overdensity whatsoever. If you have no overdensity, then you're basically limited by what you're seeing here. The other option, of course, which I show here is you could have hotter neutrinos. So if you somehow increase the temperature of neutrinos, you could maybe do that in some way similar to how you increase the photon temperature in the early universe, right? If you have something which decays to neutrinos, you can conserve entropy and go from there. That's potentially another way to get around the exclusion principle band, where you're not getting around it, but you're just living in around, a range that's allowed. But those are more or less the only two ways in which you can do it. Other than that, you can't really get overdensity as far as I understand.
Okay, thank you.
Sorry, on the last plot,
Uh-huh.
for what neutrino mass are you plotting this?
This is sorry, yeah, I didn't mention this. So I think for this one I chose about 10 millielectron volts for the lightest neutrino mass.
Okay, so on that's like on the left side of the
Yes,
previous
so
plot.
I believe it corresponds to, yeah, exactly, something like here in this white region here. I don't know if you can see I don't know if you can see my pointer, by the way. I didn't know if you could see
Yes,
it at
yes,
all.
yes.
I was using it, but I wasn't sure if anyone could actually see it. So yeah, but yeah, it
So
corresponds to about this point here.
the region of Ptolemy could improve.
Yeah, the Ptolemy's. I have my problems with Ptolemy. I know I kind of said the whole talk how it doesn't really work, and I am a firm believer of it. I think Ptolemy's a fantastic idea, but I just think that getting the 100 grams of tritium is really such a huge experimental undertaking. I can't see it happening anytime soon. I really don't see how they do it. And it was hard enough before they had the uncertainty principle issue. As soon as the uncertainty principle came along, it just, to me, completely killed it. But we'll see what they do. Obviously, there are a lot of people that work in that collaboration, and I know some of them, and they're very smart people. So I if anyone can do it, they can, I'm sure. But for me, I think it's a long way off. I think Ptolemy really has a lot of room for improvement. Like I say, when you actually include the effects of the bad energy resolution at Ptolemy, this goes up by 5, 6 orders of magnitude everywhere, and this nice region moves to the right even further, which is really, really not good. What I did want to mention, however, I didn't mention it in the talk because I didn't have time, is there was a nice paper a couple of years ago that suggested using some angular correlations or some time dependence of your signal at Ptolemy, right? So we have when you compute this amplitude, you can do so in a polarized way with a polarized amplitude, and it depends on the vector between the incident neutrino wind and the polarization of the tritium or something along those lines, right? And what you get is some time dependence in it, which means the rate has some time dependence. And then you can do a Fourier transform of your signal at Ptolemy and look for something at a very specific frequency corresponding to, say, an annual modulation or something along those lines. And you can actually improve your signal noise ratio by an order of magnitude or two, purely using that Fourier transform effect. Now, that's not enough to fix Ptolemy, but it's definitely a way in which Ptolemy could, say, get an order of magnitude better than what they propose in this region where the energy resolution is bad. And so if the energy resolution isn't perfect at Ptolemy, even if they can't get it all the way to this good, if they can get it a bit better, if they could combine it with this annular modulation thing, they can maybe at least overcome partly the issue, which is nice.
Super, super. We have actually a couple of questions from YouTube. So let me pass this on before continuing. So the first one comes from Particle Espresso.
Okay.
So the question is, when the neutrino scattering becomes coherent over the whole atomic target or many atoms, do they pick up additional screening from seeing the electron weak charge?
So this is very, very nice actually. So the way in which I've always computed this is I actually add the two things together. So I add on the electron. There are two components to it. There's the probability that they scatter off of the atomic nuclei, and there's also the probability that they can scatter off of the electrons in the target as well. And it turns out, in fact, that the electron component is larger than it's expected to be larger than the atomic scattering component by about an order of magnitude or so. So it's not so much that it's not so much that it cancels. It's more of an enhancement than anything. It adds on an extra effect. Basically, it's an extra thing that you can potentially scatter off of, and it increases the scattering rate by an order of magnitude or so, which is very, very nice.
Good. Let's see. Let's go to the last question from YouTube. This comes from Adrian. Is there a special configuration where the spins in material can be aligned in an unstable way at a critical point, such that the neutrino background have larger cross sections to induce spin flips?
I need to understand exactly.
Yeah. So I think I didn't read it properly. I didn't read it properly. Sorry. So let's see. So if there is a special configuration where the spins in material can be aligned in an unstable way at a critical point, such that the cross sections.
So something like a resonant spin flip or something along those lines.
I think so. I think so. I think that's the idea.
I mean, that sounds potential. I mean, that's a really nice idea, in fact. So the idea there would be something like a hyperfine transition or something along those lines, I guess, where you scatter a relic neutrino off of something and you go from a spin up state to a spin down state or something along that. That's my guess there. I think in theory that's possible, and I think it would actually be quite nice for the cosmic neutrino background in the sense that the sort of energy scale of these hyperfine splittings is typically of order a few micro electron volts or so. And a relic neutrino actually has enough energy to cause that kind of thing to take place. So potentially, yes, that's something you could do, if I'm understanding the question correctly. If not, I've just given away a really good idea. I don't know. But yeah,
so Adrian says that yes, that's the question.
I think so. If I'm understanding the question correctly, that sounds like something you could do, and it sounds like something that would actually be quite nice for the cosmic neutrino background. Yeah. That's my best answer to that one.
Maybe you found yourself a new collaborator.
Actually, I should probably be quiet because actually I'm working on something very similar to that at the minute. So I mean, maybe that's why I know the answer. But yeah, it seems like something that's possible. Yeah, it sounds reasonable to me.
Great. Okay, I don't know if there's any other questions from anybody here. I have one regarding following Roberto's question, right? That's a typical thing, you know. Today's signal is tomorrow's background. So in principle, how do you avoid the background coming from dark matter or from other neutrinos coming like thermal those solar thermal neutrinos? How do you avoid those backgrounds? Now we have neutrino fog, no? So
this is a very good question, and it's an experiment. You have to answer this on an experiment by experiment basis, but I can give you some examples. So the solar thermal neutrinos, I would say in general, aren't a problem because the flux of them is so low. They probably actually end up not being a background to relic neutrinos at all, purely because you have so many relic neutrinos. So that's those ones are dealt with. But that's not always going to be the case, I suppose. Other ways in which you can get away with them. So if you look at, say, the accelerator experiment, it's a resonant process. So only neutrinos of a very specific energy, i.e. you tune your beam energy precisely to the cosmic neutrino background. So any neutrino that's a higher energy won't have a resonance anymore. So the scattering cross-section will be so low that it won't act as any background to the CNUB. Other experiments, however, like the Studolsky effect or the coherent scattering, those are a lot more difficult to get rid of background. So for coherent scattering, for example, you don't ever see a weak interaction take place, right? And since you don't actually see a weak interaction, you just see some small acceleration of your target due to some uncharged particle scattering off of your target. Dark matter could very, very much be a background for that one. And the Sadolsky effect is quite similar. So if I actually wrote a paper on this a couple of years ago, the dark Sadolsky effect, where we explored basically every the dark matter, the Sadolsky effect due to dark matter for every dark matter operator. And it turns out that on average, the Sadolsky effect due to dark matter is significantly larger than it is due to the cosmic neutrino background. And again, there's no way to guarantee that effect is due to neutrinos from the Sadolsky effect. You just see some spin precession, and you know you've got basically some invisible light uncharged particle causing a spin precession. But that could be anything basically with a spin-dependent interaction that you can't see. It could be neutrinos, and probably will be. Maybe you can look at the energy shift itself, and you can, you know roughly how big you expect it to be for the CNUB, so you get something that's consistent with it. But there's no smoking gun to say that this is definitely the CNUB in that case. So my suggestion in that case is something along these lines. You build one of these experiments, and you see something that's consistent with the cosmic neutrino background. Right, so you get some I don't know, you see some acceleration at, say, a coherent scattering experiment, and from that you can infer things like, I can roughly estimate this is what my cosmic neutrino background temperature is, density, mass, and so on and so forth. I then build a second experiment, and I put it precisely at the point that this experiment was sensitive to, this point in parameter space where, so suppose with my mouse, I found a signal in this region of parameter space here. I now build another experiment which is uniquely signal to this parameter, this area of neutrino parameter space. And I look for it again with that one. And then if that one sees something there as well, now I have two experiments which have something which are consistent with neutrinos. Whereas the dark matter might only have been visible in, say, one of those experiments. That's the only way. So I think realistically, any reasonable determination of the cosmic neutrino background is going to need two experiments. Now, there are some exceptions. So Ptolemy, for example, if it works, I think you could say you've seen the CNUB with just Ptolemy on its own, because it's clearly a weak interaction, a charge current interaction. It's almost certainly a neutrino at that point. But if you don't see a charge current interaction, then probably you need two or more experiments to guarantee that you've seen it.
Excellent. Let me see if there's any other questions on no more questions on YouTube. So one final question. I think this is a very naive question. I might have to do it on paper, but I was wondering about the fact that you get twice as many events from Majorana neutrinos in this experiment, for example, as you mentioned, in Ptolemy. So I was thinking, because in principle, right, you have an initial number of neutrinos, initial number of antineutrinos, and in principle, what is conserved is helicity, right? So then each state will acquire the different chiralities, right? So I would imagine that a state could become like 1 over square root of 2 of neutrino plus antineutrino, chirality-wise. So then I would expect that each neutrino would be a superposition of the neutrino and antineutrino states, so only the neutrino part would interact, or only the antineutrino part would interact.
Okay,
so
this is very interesting.
Wouldn't cancel at some point and give you the same prediction?
No, so you end up with so it depends. This is actually a very, very good question. So this stuff that I've talked about today when I talk about Majorana neutrinos, I've been talking specifically about the seesaw limit the whole time. And in the seesaw limit, it turns out that you basically get this factor of 2 everywhere. However, there are other possibilities. So you can work in the pseudo-Dirac limit, for example, or somewhere in between, where you have the Majorana mass is very small and the Dirac mass is very large in comparison. And then these things look very similar to Dirac neutrinos, in which case what you end up finding is that the signal ends up looking like a Dirac neutrino. Even though it's officially a Majorana neutrino, the signal ends up looking like a Dirac neutrino. And I wrote a paper on this very recently, came out a month or so ago, where we explored basically all of these proposals for pseudo-Dirac neutrinos, and we showed how sensitive they were in this whole space. So that answer to your question, do these effects cancel, depends effectively on the ratio of the Majorana mass to the Dirac mass. If the ratio is very, very small, i.e. in the seesaw limit, you end up with what I've shown in this talk. If you're in the other limit, the pseudo-Dirac limit, you end up with the opposite effect, whereby you get something that looks like a Dirac neutrino, even though you have Majorana neutrinos. And there are actually some very interesting things you can say about this. So the cosmic neutrino background, for example, is capable of setting because of the sort of the way you can think of them is like active sterile oscillations, more or less. This is, I think, roughly what you're inferring, right? Where basically the active state picks up a sterile component or something that can't be seen in your detector over time. Exactly, right? You can think of this a bit like an active sterile oscillation. This is the typical way in which people sort of talk about this framework. It turns out that because the baseline for these oscillations with the relic neutrinos is basically the age of the universe or the size of the universe, it's the largest possible baseline. You can't have a baseline longer than that. So relic neutrinos are capable of setting the strongest constraint on the Majorana mass of any other experiment because you can't have these oscillations over longer distance scales than that, and they can constrain Majorana masses as small as something like 10 to the minus 33 electron volts in theory, which are absolutely absurd. So anything smaller than that will, for all intents and purposes, basically be a Dirac neutrino, and you will never be able to distinguish between the two. But yeah, this is something you have to take care of. If you actually want to do these analyses properly, which is something I didn't do when I wrote this paper and my thesis and so on a year or two ago, I worked in the seesaw limit the whole time. It was only when I started working on this other project a year ago or so that I did it more rigorously. And you find actually that you have to be very careful when you treat Majorana neutrinos. And depending on the ratio of the Majorana to Dirac mass, you end up in two different scenarios.
I see. Super. So we don't have much time. We have no more questions from YouTube. I don't know if there's any urgent question over here. We're a little bit late. Okay, so I think this is a good time to stop. So thank you very much, Jack, for the talk. It's been wonderful talking to you.
Well, thank you for having me.
Well, viewers, thank you for watching. This is the last webinar of the year. We're taking a long break and starting again in January. So I hope you enjoyed this season, and we'll be seeing you all next year. See you all soon. Okay.